Hello and welcome to Examples for You, video 2. Gosh, I hope you are watching this. I hope you tried the problems because these problems are, I'm not going to lie to you, they're kind of exciting. Okay, so just like what we did in our notes, we're finding the points of inflection and we're discussing concavity. Because they're not asking us anything about critical points, increasing, decreasing, relative extrema, we get to move to the first derivative, which would be 8x to the third minus 8, and then right to the second derivative, which would be, yikes, 24x squared. There's no place where it's undefined, so I'm going to set it equal to 0 and find that point. That's going to be at x equals 0. That's not a point of inflection. That's a possible point of inflection. I feel silly putting PPOI, so I just don't write anything yet. Put your little 0 on there. Well, if I pick a -1, if I put -1 in there, -1 squared is positive. 24 times a positive number is positive. If I put a positive number in, I get a positive as well. My second derivative is positive all the way through. Okay, 0 is a point on our graph. So my derivative is greater than 0 from -infinity to positive infinity. So my original function is concave up on that interval. I don't have any place where my second derivative is negative, so I have no concave down. We still need to talk about if there's any points of inflection. Remember, to be a point of inflection, you have to change concavity. I don't change concavity, and you need to write that in there. You can say G, put in a since, that sounds good. Since G is strictly concave up, there are no points of inflection. Whenever you're talking about points of inflection, you must talk about a concavity change. So if there's no concavity change, no deal. Our second example for you deals with some trig. Now, trig can be kind of tricky because there are so many possible points of inflection. There are so many possible relative extrema. So it's always nice when you see that they've cut us down to an interval. It's also nice when it goes from 0 to 2 pi because that's our normal 4 quadrants. We just feel a little safer there. Find our derivative. Unfortunately, we've got sine and cosine, so we just kind of jockey back and forth, but at least we don't have something like secant or cosecant that just keeps getting bigger. So I guess we should be thankful, but it's not as good as a polynomial that gets smaller. So when I take the second derivative, I have my minus cosine of x. Okay, I need to set that equal to 0. I'm going to go ahead and solve, so I'm going to take my sine of x to the other side. Do not divide through by a negative. You need that negative to figure out your concavity. So don't divide anything away. Keep it, use it as part of the factor, etc. So I'm looking for where sine is equal to the opposite of cosine. Well, sine is equal to cosine at the pi over 4s. So the related angles. When I'm looking at my quadrants, everybody's positive, only sine, only tangent, only cosine. I need to know where they are opposites of each other. Well, they have the same sign in quadrant 1 and quadrant 3. So opposite would be in quadrant 2 and quadrant 4. Those possible points would be 3 pi over 4 and 7 pi over 4. When I do my number line, I do the same thing I did before when I had a domain restriction. I make sure that I put those in there because I do not want to be caught talking about things that aren't in my interval. So I don't want to whip out a positive infinity here because that could cause us some problems. All you need to do is pick a point that's in that interval, put it into your second derivative to see if it's a positive or a negative. Okay, well, in this interval, I've got a lot of things that are in the first quadrant. So if I look at an angle that's in the first quadrant, okay, it is going to be, my sine's going to be positive, my cosine's going to be positive, so that's going to be negative, negative, and it will alternate. Okay, so you can pick a point in between, pick any special angle you know the value of. So I do have two intervals where I'm negative, one interval where I am positive. And any of those intervals where you're negative, you can put those all together. Okay, now I just put f double prime. Why would that be a problem? Because our function's name is h. It's a little thing, but you got to make sure you're calling the function by its proper name. So my second derivative for h is less than 0 from 0, and you can do open intervals or you can do closed intervals, it doesn't matter. And 7 pi over 4 to 2 pi. So h is concave down from these intervals. Now, I know some of you are going to ask, gosh, do I really need to write them out every time? Can I just put ditto marks? Can I just forget it? No, we have to write them because we need to practice. We want to make sure that we are always writing them when needed, because on a free response problem, if we don't address this, we won't get points. Because this little guy right here is worth no points at all. It's to help us stay organized. Your points are coming from these justification sentences. So please practice writing them because they are worth your points. So our second derivative is positive from 3 pi over 4 to 7 pi over 4, which means our original function is concave up from that same interval. Okay, there is a change in concavity. I've run out of sentence room, so I'm going to come up here. Okay. I apologize that everything's kind of jumpy, but something's wrong with the program. The mouse is strobing, so it makes it difficult to write. I'll turn the mouse off so you don't see that strobe. Okay, h changes concavity. At x equals 3 pi over 4 and 7 pi over 4. So x equals 3 pi over 4 and 7 pi over 4 are POI. Now I know you want to use words like their points of inflection, it is a point of inflection. Stay away from those particular statements because it could be first derivative, second derivative, critical points, POI, everything. So we need to make sure that we're explaining what it is. Okay, so we had our notes, oh, the good old days. Here is our second derivative test to locate relative extrema. So we need to find the first derivative, just like we did before, but this time we need to wait and find the critical point, then go through and find our second derivative. So our first derivative is going to be 2 cosine of x minus 2 sine of 2x. Remember your chain rule. Now that's wonderful, but in order to solve for 0, we're going to need to use our double angle formula. So remember that the sine of 2x is 2 sine of 1x, cosine of 1x. When we make that substitution, we're going to have 2 cosine of x minus 4 sine of x cosine of x. When I set that equal to 0, I'm going to factor out a 2 cosine, which is going to leave me with 1 minus 2 sine of x. When I set each one of those equal to 0, well, cosine of x equals 0 when x is equal to pi over 2 and 3 pi over 2. Think about the graph of cosine. And I literally just think about my graph. Bonk, 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 bonk. Sorry about the noises. I've got to do it. Cosine starts up, then hits 0, goes down, hits 0, comes back up. These little 0 marks, pi over 2 and 3 pi over 2. Here we're looking for where sine of x is equal to 1/2. That's our 30-degree angle, our pi over 6. Sine is positive in the first quadrant, which would be pi over 6, and in the second quadrant, which would be 5 pi over 6. This one's a good one to do our second derivative test because we don't have to write sentences for it, which makes it a lot nicer. Let's not use purple, let's use red. So finding our second derivative, we'll want to go to the original where we have our 2 sine of 2x, not to the 2 sine of x cosine of x, because that creates a product rule that many of us don't want to do. When I take the derivative of 2 cosine of x, that's negative 2 sine of x minus 4 cosine of 2x. The derivative of negative 2 sine of 2x is negative 2 cosine of 2x times the derivative of your angle, which is 2, so that's how we got our 4. Now remember, with our second derivative test, I only have to plug in these critical values. So I have to plug in my pi over 2, see what happens, my 3 pi over 2, see what happens. Don't forget to show what we're doing, so make sure you put your 2 hash marks, pi over 6, and then 5 pi over 6. Now this is not out of the question for them to ask us to do this without the use of a calculator. I'm not going to go through that, but if you want me to, I'd be happy to address that in class. So at pi over 2, I should get 2, which is greater than 0, so that one's a relative min. Okay, this we get 6, so that's greater than 0, so that's a relative min. Pi over 6, that's negative 3, which is less than 0, so that's a relative max. And then this also gives us a negative 3, which is less than 0, which is a relative max as well. Okay. Now, if you want to know what those actual values are, remember your relative max is a point. That would be 5 pi over 6. To find the y-coordinate, you'll need to plug that back up into the original. So you would plug it in right here for your x, right here for your 2x. If you wanted to do that, they asked you what was that relative max, that would be a 3/2. Okay? So remember, these are relative extremas, doesn't mean it's the absolute. Okay? So our second derivative with trig functions, you have the opportunity to have many, many more than you want. But we know there's going to be a finite number because they did shorten us here. Okay, I'll see you in class for that last example. I know you're excited about that. So I'll see you back at class.